Tunnel boring machines, applying non-destructive testing to verify grouting processes of tunnel lining with Sydney Metro. My name is Stephanie Palmer and I'm a civil and environmental engineering student. Whilst working at Sydney Metro City and South West, I became absorbed in this once-in-a-generation tunnelling project. The scale was captivating and the enduring impact that it would have on shaping how Sydney-siders viewed public transport was tangible and exciting. In particular, I was intrigued by the structural fundamentals supporting tunnels, which are in fact monolithic underground structures. Sydney Metro City and South West is Australia's largest public transport project, comprising 15 kilometres of circular twin tunnels, each with a diameter equivalent to 2 stories of an office building. Tunnel structural integrity relies on the segmental concrete lining. Concrete tunnel lining distributes external soil pressures across the circular tunnel shell. Safe tunnel design is reliant on the uniform contact between this lining and the surrounding soil. Uniform contact is achieved by filling the circular or annular space between with grout. Any voids in the grout at this interface negate the purpose of this filling. However, undertaking quality control of the grout is challenging as the final product cannot be visually inspected. Internationally, the accepted industry process to verify the completeness of grout in the annular gap is flawed, as it compromises the concrete lining by destructively drilling through it. To visually observe the gap, an endoscope is threaded through a hole drilled through the concrete lining. In other words, the only way to quantitatively check the annulus gap is to destructively drill. This destructive method compromises the waterproofing properties of the tunnel lining, has the potential for cracking the tunnel lining, and as you can see by these pictures, only provides a very restricted view of the annulus. Given the inadequacy of the current industry standard, an opportunity to trial an alternative, non-destructive solution was presented at Sydney Metro. Responding directly to this commercial significance, my capstone will investigate the slab impulse response method, innovatively repurposing an existing technology used in pile inspections as an alternative, non-destructive tool to assess grout quality behind tunnel lining. The slab impulse response method uses the impact of a rubber-tipped hammer to send low-strain waves through the test element. Once hit, the test element acts in a bending mode. The movement, or bending, is received by a geophone, or velocity transducer. The load cell built into the hammer measures the force signal, and the geophone measures the velocity response. Both the hammer and the geophone are linked to a portable computer for data processing and storage. If no void exists, the grout or soil behind the tunnel lining acts as a dampener to reduce bending in the segment. However, if a void does exist, the segment will not be supported behind the lining and therefore there is no media to produce a significant dampening effect. The presence of voids increases amplitude of vibrations and is measurable using the method proposed in my capstone. The main challenge was to develop a methodology to verify the presence of grout behind the concrete segmental lining. Typically, data verification requires determining whether the data produced by the slab impulse response method accurately reflects the state of grout concealed behind the concrete tunnel lining. Thus, verification monitors inconsistencies between the quantitative data from the slab impulse response method and the qualitative data through observing the grout. Gathering qualitative data would require visual inspection of the grout behind the concrete lining. However, the only way to visually inspect is to destructively drill. The consummate cost and risk is precisely what my thesis aims to reduce and improve upon by examining the slab impulse response method. The challenge for me was presented to shift my thesis focus from validating each and every data point by drilling to identifying another measure of success for the slab impulse response method. Ultimately, I determined that assessing the accuracy and repeatability of the non-destructive slab impulse response method was critical for confident in situ real-time testing. I decided that the best way to measure accuracy is through what I call first-time right cases. That is to say that I linked actual grout volume data to the slab impulse response data. In addition, to assess the repeatability of this testing method, I analysed the variance of results. My aha moment came during my research when, trawling through numerous academic and industry papers from around the world, it became clear that there were limitations to all methods currently used to verify the presence of voids in the grout behind tunnel lining. Thus, there was a genuine commercial need for a more effective and accurate method. I was spurred on by the realisation that my research at Sydney Metro had an opportunity to significantly contribute to the safety and quality of future tunnelling projects globally. Industry interest in the slab impulse response is driven by significant efficiencies in cost, time, and labour savings, which together improve safety and commercial outcomes. The slab impulse response is able to rapidly sample a large area of tunnel and provide an indication of areas with voids in the grout. This enables the number of drilled points to be targeted to only those with incomplete grout, thereby dramatically reducing the number of drilled holes and consequently the time and cost involved in the labour-intensive process to repair, reseal and waterproof the holes after drilling. Of equal commercial significance is the fact that drilling requires machinery which stops all other tunnel traffic and stops tunnel production completely. Both tunnel production rates and quality control are linked to financial incentives and are therefore commercially significant. The innovation behind the slab impulse response stems from repurposing an existing technology and adapting it to a new context. This enables it to be readily introduced to the tunnelling industry. The slab impulse response represents an improvement on an existing process by providing a non-invasive picture of the grout behind the segmental lining. My capstone will uniquely contribute to the breadth of understanding of the slab impulse response in a tunnelling context, which to date has been limited globally to a handful of projects in Argentina, the United States and Denmark. Increasing urbanisation will necessitate more underground infrastructure globally and hence more tunnelling. Safety will remain paramount and hence the benefits of cost savings with respect to grout verification will only become more relevant. It is my hope that, given the number of tunnelling projects forecast in Australia alone, there will be more opportunities for in situ testing, increasing the pool of data and enabling us to quantify the benefits the slab impulse response can deliver both commercially and for the long-term structural integrity of our tunnels.